Okay, so hi everyone. My name is Kyla Koch. I am a physics and math double major from Baldwin Wallace University, maybe 20 minutes south of Cleveland Clinic main campus. And I was placed in the biomedical engineering department, more specifically in the Jiaozhuan Li lab, where this lab focuses a lot of its time on medical imaging. So just to go over what my project exactly was, it was relating to image segmentation. So image segmentation is a pretty common practice in magnetic resonance imaging. And we implement it by selecting parts of an MRI scan and extrapolating the area of interest. Segmentation speed and precision are important for patient diagnosis and are a pretty ongoing field of research, just because as we come up with new algorithms and improve the performance, we want to keep becoming more precise with our segmentations and make sure we're doing it at a good speed. So our research uses something called the inverse quantum Fourier transform, which I'll commonly refer to as the IQFT. So this algorithm is used to exploit the speed and problem-solving capabilities of quantum computing in order to improve automated segmentation of MRIs. So when you segment an MRI, you can do it manually by, let's say, with this original image down below. This is an MRI of a knee. And let's say we wanted to focus on the cartilage. We could go into that image and manually cut out all of the pixels of cartilage in the image, which would be very time consuming and it might not be very precise. However, we could also, instead of the time consuming way, we could implement an algorithm, and this algorithm would automatically just take out everything we need. So we would automatically take out all the cartilage. So that's kind of what our algorithm is trying to do. So our IQFT is theorized to provide more accurate images for radiologists to diagnose patients and show how quantum computing can advance healthcare. So this project took a long time to lead up to. So we started at a very basic ground level by trying to figure out how exactly can we encode classical data into something a quantum computer can handle. So the first project I did was encoding a scalar. So we just wanted to encode some kind of integer. For example, we did the number 5, and this was a project that I did previously over the past year at my university. So we encoded the number 5, applied the quantum Fourier transform to it, just simple algorithm, applied the inverse, and then we got back out the number 5 about 85% of the time, which is pretty good. Next, now that we can encode one number, let's see if we can encode multiple numbers at the same time. So we encoded a vector. More specifically, we encoded 127 sign values, applied the quantum Fourier transform, applied the inverse, and then as you can see in this sine of x QFT circuit graph, we get a sine wave back out, which is exactly what we wanted. Next, we wanted to encode an image. Since we're going to be dealing with images and MRIs, we were able to do that as shown right below the sine QFT circuit graph. So we encoded a pretty basic image known as Lena 64. It's just a 64-bit image. And we were able to encode the image, do the quantum Fourier transform, do the inverse, and we get Lena back out as shown. We can measure Lena using counts, or we can measure Lena and keep it just in terms of the state vector, which encompasses all of the complex values and probabilities. If we measure Lena in terms of the state vector, we get basically the exact same image back out. But if we measure in terms of counts, this takes minutes to run. And even when we do millions of trials, we don't exactly get the same image back out. In fact, we get a little bit darker of an image. But by measuring the state vector, we find that we can get approximately the same image back out. Next, we implemented the inverse quantum Fourier transform segmentation algorithm, and that is shown below in the images I noted before. And then we also wanted to implement error mitigation techniques. So when we are at a level where we can run these algorithms on IBM hardware, we will apply mitigation techniques, which will just give us more precise and accurate outputs. So below, like I said, there is the outputs of the segmentation implementation. So like I said before, we used a scan of a knee and we just wanted to extract the cartilage. So here in the inverse, the IQFT segmentation, we have just the cartilage that was pulled out, which is very nice. But we have some spots where maybe to the little bit of the right, if you can see, there's a little island that's poking out that's not cartilage, it's actually muscle tissue. So we're still trying to perfect this algorithm performance. So some outcomes of the project were that we were able to actually convert MRIs into data that can be stored and manipulated by a quantum computer, which is a huge step. We can also segment MRIs using a quantum-inspired algorithm. It does not use Qiskit, but we're trying to get to that level where we can actually simulate it on either hardware or use it on a simulator. So we can use this inverse quantum Fourier transform to analyze areas of interest. And like I said before, we analyzed the cartilage. Moving in the future, we would like to, we're working on using qubits to encode additional information about quantitative MRI measurements. So we want to, instead of encoding grayscale values like the inverse, the IQFT algorithm uses, we want to encode T1, T2, and other physical attributes of MRIs. Like I said before, we also want to use this algorithm on IBM hardware, which may make things more precise. It might speed things up a little bit if we have all of these different dimensions, such as T1, T2. And then we want to quantitatively compare quantum segmentation algorithm performance to the classical performance. So below we have the inverse quantum Fourier transform segmentation, which is quantum inspired, but we also have alongside the k-means clustering and O2 thresholding, which are pretty common segmentation algorithms, but they are purely classical. So we can see that even these algorithms have some issues with segmentation, but we would like to quantitatively compare how the IQFT performs against the classical algorithm performances. So that's all I have. Thank you for listening and have a great day.